Hello everyone. Today we're going to talk about a very small topic that has been on my mind for a very long time, and it's about loss functions. So whenever a model makes a prediction, especially in supervised learning, it needs to be compared with the actual result. And basically, the difference between these two values is what loss is. Basically, it's telling the model that how far off we are from the actual prediction, and the result is our loss value, which we can use for backpropagation and teaching the model how to improve itself. So let's say there was a loss function. So this was our model connected to the loss function, and we would give it x being the prediction made by the model, and then we give it to the loss function. It compares the predicted value with the actual value and gives us a value of how far off we are. Now sometimes the loss is a convex function. Convex function basically meaning it looks something like this. In such situations, there is one global and local minima, but sometimes the loss function is not a convex function. So the function can look something like this, in which there are various points which can be considered local minimas, and then there is a global minima. So global minimas are basically these points which are the lowest point in the function, and if we can get to this point, we would theoretically have the lowest loss, meaning we would theoretically have the best model. On the other hand, we could potentially get stuck in these minimas, and we would not have the theoretically best model we can have. Now, if we visualize our function into something that takes two values, for example, a model that takes two inputs, A and B. This could be a weather forecasting application that would take the weather of the previous day and the temperature of today. So that would give us a loss function that would look something like this. Now notice how there are multiple points that can be the minima, and this graph keeps on going, so we can potentially have infinite number of local minimas and one global minima. In just using this two-dimensional data, the complexity has jumped so high and has made the process of finding a best case global minima so much more difficult. Now, the question might be, are there any methods or techniques to find the global minima effectively? And the answer is there have been a lot of attempts and a lot of good technological or theoretical advancements in finding the best minima for a model. These methods are stochastic gradient descent, momentum atom, learning rate scheduling, all these methods. Currently, one of the most commonly used optimization algorithms can be considered to be Adam, and that is because Adam is very effective at finding very low minimas. So, Adam, with its optimization, will be able to find a minima that is very close to the global minima, or it might find the global minima itself. To learn more about these optimization techniques, I would recommend studying each one from the ground up, because each optimization technique is built up upon the previous one. So you have to first study stochastic gradient descent, then momentum, then Adam, and then the next optimization techniques. Now, a particular method that catches my attention is random restarts. What does random restart mean? Random restart basically means that you start optimizing, basically you reinitialize the model over and over again until your model starts from a point where it's reachable to the nearest minima. And in doing this, you luckily end up finding the global minima. Now that brings us to the question, is training a deep learning model a luck-based activity? I would say to a certain extent, yes. Because I'm not sure, and I believe we haven't found a foolproof method to find the global minima of a model efficiently. And why is it difficult? Well, number one, most loss functions are not convex, meaning it's very, very, very difficult to find their local minima versus their global minima. Second point is the high dimensionality. When you're giving a loss function a output of the model, these days it's a lot of it can be embedded information or very high dimensional information. For text, it could be 62 embedding and just large amounts of data. And so this increases the dimensionality of the loss function, in turn increasing the complexity of the loss graph. So with just one dimensional input and one dimensional output, we have this graph. With two-dimensional input and one-dimensional output, we have a 3D wavy functional output. As we keep increasing the input and the output size, the graph is just gonna get more complicated and more harder and harder to navigate through. And that's why it's very difficult to design a very easy, simple, optimal algorithm to find these local minimas and global minimas. I believe this is an ongoing journey, and in the future we will have more advancements towards better optimization techniques, and we will be able to do better in finding these global minimas. But till then, we have our optimization algorithms, our random restarts, ensemble methods, and we're doing pretty good with them. In all conclusion, I made this video because I have faced a phenomenon where I train the same model with the same data set multiple times, but the loss value I get and the accuracy and the F1 score I get is different every single time. And so it begs the question, how many times do I train my model until I get to a point where I can positively say that this is the best my model can do, and this is the best my model can perform? Because we don't know for sure if that is the local minima or the global minima, and the thought that I will not be able to find the most optimal solution and my model will not be able to live up to its full potential breaks my heart in some ways, because it really stresses me out when I train a model and it has such low accuracy on the first turn, and then I retrain it and the loss value goes down. I mean, it goes up. Lower loss means better models. So I train it again, but the loss value goes up, and that's really frustrating. And so I believe this is a battle all machine learning and deep learning model enthusiasts struggle with on a daily basis. And that's why I wanted to make a short video about it. That's all from me. Okay, bye.